Hello everyone, welcome to the presentation of our paper. I am Adnan Rakin from Arizona State University. This is a work produced from Mitsubishi Electric Research Laboratories. The title of our paper is Towards Universal Adversarial Examples and Defenses. In this work, we mainly propose an attack algorithm that is independent of any model information. We exploit the underlying vulnerability of the data distribution to generate the attack. In addition, we also propose a defense method. Next, I will present each component of our attack and defense in the next slides. Before going into the details of our attack, I'll present the background of adversarial input attack. It is basically the natural data maliciously perturbed by human imperceptible noise, but can cause the malfunction of neural network with erroneous prediction. Here we present a simple adversarial attack known as fast gradient sign method. In fast gradient sign method, the attacker takes the clean data and adds a perturbation. The perturbation is scaled by a parameter called epsilon, that is basically the L infinity norm, and the scaling factor is the sign of the gradient of the loss function of the neural network with respect to the clean label. Once the attacker adds this noise to the clean data, he can produce an adversarial example. There are many other popular adversarial attack algorithms. Among them, projected gradient descent (PGD) is very popular. In this work, we mainly focus on the PGD algorithm, which is a multi-step iteration of the FGSM attack. On the right figure, we show some popular examples of adversarial attacks. For example, a panda image is being misclassified to a given class with adversarial noise. On the bottom row, we show an example of adversarial attack on speech recognition algorithm. Adversarial vulnerabilities have been also demonstrated in practical applications. For example, a Tesla Autopilot system can be fooled by small stickers on the ground. It can fool the computer vision algorithm into causing misclassification. There have been extensive research on defending adversarial examples. Among them, the most popular one is adversarial training. For example, in PGD training, the defender can always train the model with both clean images and adversarial images to make the model learn and adapt to the adversarial noises. This is a very popular algorithm in defending adversarial examples. There are also other regularization techniques, for example, adding noise during the training. Other defense methods have followed non-differentiable functions during the forward path. However, non-differentiable function causes gradient obfuscation and does not fundamentally defend the adversarial attack. Input preprocessing is also another way of improving the robustness. However, feature scaling and other methods of input preprocessing have also been shown to be vulnerable against strong adversarial attacks. The real weakness of these methods comes from the training expenses. For example, if someone has to train the model with PGD training, that comes with double training cost depending on the attack being used to train the model. And these defenses are not general across attacks. It can defend one attack and fail against the other. Also, the gradient obfuscation methods gives a false sense of security. They actually do not improve the underlying vulnerability of the model. They just gives a false sense of security or defense. In the literature, we find two kinds of adversarial attack. First, white box attack, where the attacker knows every information of the target DNA model. Second, black box attack. In our adversarial attack setup, we basically focus on the domain of black box attack. That is why it is very important to clarify what exactly is a black box attack. In our threat model, we assume the attacker do not have access to model architecture, model weights and biases, training data, gradients, or even the output prediction or logics. All the attacker have is a set of sample test data, using which he needs to generate the adversarial corresponding samples. In a traditional substitute black box attack, the common approach was to train a substitute source model. Using that substitute source model, the attacker can always compute the gradient because the substitute sort model is a white box to the attacker. Using the gradient computed from the source model, the attacker can generate the adversarial noise corresponding to the input samples. Then the attacker will add that noise to the incoming input data and fool the target black box DNN model to hijack the functionality. We want to perform black box attack on a target black box model, but our attack needs to be universal or independent of any model information. What do we exactly mean by universal adversarial examples? By universal adversarial example, in this work we mean the generation algorithm is independent of any model architecture information. It only utilizes the underlying vulnerability of a given data distribution, and the attacker can only use the accessible test data available to him. And also, at best, it can potentially transfer between different models. The potential benefit of this universal attack would be it would reduce the attack cost. Also, it is model independent adversary, so it can speed up the adversarial training. Why? Because since the adversarial generation is model independent, the attacker does not rely on any model specific information to generate the adversary. So just by generating one set of adversarial samples, he can train a million models. Also, the attacker, as I said, the attacker just needs to generate adversary once for a given dataset and can attack countless model and can defend countless model. Hence, to generate universal adversarial examples, we follow a two-step training algorithm. In the first step, which is an offline training step, the attacker trains an offline generator to learn to produce adversarial example. In the second step, the attacker takes this pre-trained generator to produce as many as adversarial examples and attack a target black box model to hijack its output. In our universal defense is basically training a model with adversarial samples generated by our UAE method. So we use this adversarial generation algorithm and train a particular model using our generated adversary and make it robust against a universal set of attacks. First, I will describe the offline generator training algorithm. To propose an algorithm for offline class conditional generator training, first we draw a connection between robust optimization and minimization of mutual information. We demonstrate how to minimize the conditional entropy by updating the parameters of the generator empirically. We put together a training scheme for the generator to achieve efficient universal adversarial generation. In the next few slides, I will go into the details of each one of them. The robust optimization problem that I showed in the last slide can be reformulated as a min-max of expectation of minus log q y given z. This is basically considering a strengthened adversary allowing mixed strategies, and the perturbation is captured as a channel. Qy given z is the given decision rule. Interestingly, we can swap the min-max to make it max-min. After making max-min, we can reduce the overall optimization problem into a maximization of conditional entropy. This maximization of conditional entropy can be further reduced into a minimization of mutual information. The overall, what we demonstrate here is the robust optimization problem is actually boils down to minimization of the mutual information between the classes of a given data distribution. The next question is how to minimize the mutual information. We train an offline encoder z theta to minimize the mutual information. We avoid direct computation of mutual information here. Instead, we adopt a mutual information gradient estimator to estimate the gradient of the mutual information. However, even then, the computation of the gradient is not straightforward. To simplify it, we follow a similar approach from Wang et al. We apply a change of variable z, which is generated from the generator using the clean data x and its label y. Then we can estimate the gradient of this term directly from the generator. However, we still need to compute the gradient of the implicit distributions. To compute the gradient of the implicit distribution, we use spectral Stein gradient estimator SSGE. Let's look at how the overall training works. The training starts by initializing the model parameters for the generator theta. Then we take a sample test batch. We apply the test batch to the generator to get an output adversarial samples. Using those batch of samples, we can estimate the gradient of the implicit distribution using SSGE. After that, we iterate through each class. From each class, we draw a sample of test images. Using those images, we can estimate this conditional gradient of the implicit distribution using SSGE again. Once we have these two terms, we can just plug them in on equation 9 and compute the overall gradient of the mutual information. Using the gradient information, we can perform a gradient descent step to update the generator parameter theta. Once the generator is being trained, this generator can generate universal sample that is independent of any given model type information. So after the offline stage, the generator could generate adversarial samples with minimum computation. Before presenting the evaluation of our attack, let me first introduce the baseline method that we will primarily compare our attack with. Our attack follows the bottom figures topology, and the traditional substitute model attack follows the top figures topology. In a traditional attack, as I explained already, the adversary trains a substitute model and then generates the adversarial noise from the substitute model to attack the target model. In our case, we train an offline generator, and that generator, after being trained, can generate online adversary at will without any gradient computation. To make the comparison fair, we will make sure the substitute training model and our generator has similar complexity. In this slide, we present our hardware and training configuration. In addition, we also present the configuration of the PGD attack that is being used to evaluate the black box substitute model. We have mainly two evaluation metrics. First is the accuracy. By accuracy, we mean the percentage of test samples correctly classified by a given classifier. The second metric is the accuracy under attack. By accuracy under attack, we mean the percentage of adversarial test samples correctly classified by a given classifier, where each sample is attacked with adversarial noise before feeding them into the classifier model. In our evolution, we have three kinds of model. First is the clean model. By clean model, we mean during training, it only uses clean training samples. Whereas PGD trained model during training uses PGD samples generated by PGD attack. UAE training means during training, the model uses our attack generated adversarial samples. We present the visual images of our attack across different L2 norm. As the norm increases, the images becomes difficult even for a human eye to recognize. This proves that our minimization of mutual information across classes is actually generating effective adversarial samples. In the table, we report the accuracy under attack after attacking a clean model with 99.2% test accuracy. It clearly shows at low L2 norm, the substitute model attack actually outperforms our attack. But as the epsilon keeps getting higher, our attack achieves on par or better results than the substitute model attack. However, the real strength of our attack is the efficiency, not actually the attack performance. In terms of attack performance, it performs on par with substitute model. However, in terms of attack efficiency, it actually outperforms it. We'll discuss the attack efficiency side in the next few slides. In the bottom figure, we show the efficacy of our attack even in a white box setup. So to evaluate that, we attack a PGD trained model using PGD attack, and with PGD attack initialized by universal attack. So in the blue curve case, we basically take our attack generated images, and on top of that we run a PGD attack. So both the attack efficiency is similar in this case. It clearly shows that with our initialization, the attack strength increases significantly in comparison to just using PGD attack. In this slide, I present the defense evaluation of our universal defense. To evaluate that, we train three different models. First, we train a model using our UAE adversaries in the blue curve. Second, we train another model using black box substitute model generated adversary in the green curve. We also train a clean model in the purple curve. Then we attack each of the model using PGD attack. Interestingly, black box training actually makes the model even more vulnerable in compared to a clean model. In contrast, our UAE training actually makes the model, the clean model, significantly robust. And this observation is consistent across different epsilon. As we observed, even by training with a higher epsilon, actually a model trained with our adversary can hold on to 25% accuracy even at epsilon of 0.2. This shows significant improvement in robustness in comparison to the baseline cases. As explained already, our attack is highly efficient. Our attack is 12 times faster than a PGD attack on a single model evaluation in our platform. In addition, even in a white box framework, attacking a model with PGD attack that is initialized with our adversary would yield a 1.5 times efficiency. What we mean by that is by using 1.5 times less number of attack iteration, our universal initialization can achieve the similar attack efficacy as the PGD white box attack. In addition, in terms of the defense, training a model with our adversaries would yield a similar cost in comparison to training 100 models, 1000 models, or so many models. It is because we need to train the generator just once. After that, we can generate a universal set of adversaries that will be universal across all the models, and we can train any number of models using those adversaries. In summary, we present a novel framework for generating model-independent adversary. We leverage the connections between robust learning and generalized rate-distortion theory to exploit the underlying vulnerability of the data. Proposed UAE trains an offline generator via mutual information gradient estimation. It generates fast, effective, and model-independent adversarial examples. We show the utility of these adversarial examples towards training robust classifiers. The defense shows considerable speed up over conventional methods. Thank you everyone for attending our presentation, and I will take any questions or you can contact any of the authors if you have any specific question. Thank you very much.